So good morning, everyone. It's Dorotea Iovino speaking today to introduce with great pleasure Chiara Goglio, that will present her work on the impacts of tidal forcing on the dynamics of the Med Sea. Chiara holds a master's degree in theoretical physics from University of Pisa in collaboration with the National Institute of Geophysics and Volcanology. She gained experience on the operational workflow and post-processing modeling chain, working on meteorological analysis and air quality forecast. That's the ARPA, Friuli Venezia Giulia. Chiara joined the CMCC in 2019, and she's currently in the Future Earth, Climate Change and Societal Challenges PhD program, University of Bologna. And her research aims to analyze the Mediterranean Sea circulation with a specific effort on understanding and simulating the tidal dynamics. Today, Chiara will present the improvement on the near real-time operational forecast system for the Med Sea, providing a description of the characteristics of tides in the basin, the implementation of this physical process in the forecasting system, and the impact of the system skills. And Chiara will also assess the effect of tides on extreme events with a case study of Acqua Alta event in Venice. I will take a few of your minutes to give you an overview of the CMCC Foundation. Our research center, whose mission is to investigate the climate system in a suite of aspects to explore the interaction of climate change with the ecosystem and society. CMCC develops models to simulate climate prediction and projection, and supports both adaptation and mitigation policies based on scientific knowledge. CMCC was born as a consortium and then became a foundation in 2015. And its members are international organization, research center, and Italian university that complements our expertise in different directions of climate science. It's organized as a network of research entities distributed across the national country, with the head office located in Apulia in Lecce, and 6 other locations that includes Bologna, where Chiara and I are sitting today. This location hosts 9 thematic divisions that work together addressing a range of scientific questions, all relating to climate science. They interact strongly with each other by studying and modeling different components of the air system, atmosphere, ocean, cryosphere, biogeochemistry, up to the risk assessment and possible solution for the future of the global environment and the economy. Some divisions deal with the development of technical and numerical tools that are necessary to model climate change in the past, present, and future from a physical and anthropogenic point of view. Another strength of the foundation is the Supercomputer Center. That is operational since 2008. It's located in Lecce and is the most powerful computational facilities in Italy, and is among the most advanced in Europe. It continuously updates with new computational machines architectures and data storage system. Also worth of mentions are the activities of dissemination and communication of the CMCC research, as well as our commitment to educational program, such as PhD program, dedicated schools, and trainings planned for students and early career scientists. Having said that, let's go back to the seminar, which will be recorded and will be then available via the CMCC YouTube channel or on the CMCC website. For any issue, you can drop an email to webinar@cmcc.it. And please don't forget, for news and updates on climate science, don't forget to follow us on social media. If questions arise during the Chiara's presentation, please write them into the QA session. You have a button on the bottom of your window, and I will give you, I will make the question for Chiara in the end. If you want to speak by yourself, you can raise your hands and I will try to give the word. Chiara, if you're ready, I can just share I can stop sharing the screen and you can go on with your presentation.
Yes, thank you, Dorotea. I'm sharing my screen. Okay, so as Dorotea briefly introduced, the topic of this webinar are the tides in the Mediterranean Sea. I will introduce you the main feature of this, and then describe how we introduce and explicitly described the tides in our numerical models. Then I will focus on the main impacts of tides on the general circulation in the Mediterranean basin, as well as I will try to explain how tides can contribute also to a specific type of extreme events that are the Venice Acqua Alta events, which I will define in the next slides. In general, the tides are oscillation of the sea level. Here in the upper panel, you should see a video, a movie showing the hourly tidal sea level signal, while the lower plot depicts the time series of the tidal sea level at Taifa tide gauge, which is very close to Gibraltar. What we can see is that tides in the Mediterranean Sea are small with respect, for example, to the tides in the Atlantic Ocean, which can reach 1 meter. But however, they are known to affect the general circulation and also have impacts on the dynamics of some extreme events, as I will show you in the few slides. In general, tides are due to the gravitational attraction of Moon and Sun on the water mass, especially in areas where we have a deep bathymetry, for example, in the Ionian Sea. Moreover, the tides in the Med are influenced by the tides incoming from the Atlantic Ocean through the narrow Strait of Gibraltar, which affect mainly the Alboran Sea, so the area very close to the strait. Moreover, in some areas, tides are enhanced by resonance phenomena and interaction with the bathymetry. This is true, for example, for the Gulf of Gabes and the North Adriatic Sea. When dealing with tides, we usually split the sea level signal into tidal components. Each tidal component is defined by its own frequency. Here in the table, you can see the periods characterizing the main 8 tidal components in the Mediterranean Sea. Each tidal component is characterized by an amplitude and a phase, which can be obtained from the tidal sea level signal applying the inharmonic analysis to the sea level. Moreover, we can say that in the Mediterranean Sea, the semi-diurnal tides are the dominant one. But we can find some areas where diurnal are also relevant. For example, in this map, you can see the blue areas, which are the areas where the amplitude of the diurnal components is even higher with respect to the amplitude of the semi-diurnal tides. There are also points for each tidal component, the amphidromic point, which are characterized by a strong phase gradient. These correspond to the nodes of each tidal component wave. So this means that in these points we have a small amplitude and a strong phase gradient. And are points which are particularly difficult to be modeled because of this strong gradient. The framework of all our analysis is the Copernicus Mediterranean Analysis and Forecasting System, the MedFS. which is composed by the NIM hydrodynamic model with a horizontal resolution of 1/24 of a degree, which at this latitude is about 4 kilometers, which is coupled with a wave model. And the system also includes a data assimilation scheme, the Ocean VAR, which provides the best initial condition for our forecast, which operationally produce analysis and 10 days forecast for the whole Mediterranean basin. We implement 39 rivers. The system is forced with the ACNWF atmospheric forcings, and lateral boundary condition at Atlantic box and Dardanelles are provided from the global. Since version 6 of our system, we include a tidal potential in the dynamic equation. This means that the tides are explicitly represented. So with respect to the previous system, what we did is to include a tidal potential. We choose to include the main 8 tidal components in the Mediterranean Sea. Then we have to include an additional forcing, which is composed by the tidal elevation and the velocities in the Atlantic box. And these are provided from the FES 2014 and TUGO models. Moreover, we changed the time integration scheme and time filter, as well as the time step. This is all aimed to increase the numerical robustness of our model. And we removed the bottom turbulent kinetic energy background, which is a parameterization of tides and should be removed when we explicitly represent included the tides. Moreover, we had to tune other parameterization. For example, in Gibraltar and Messina, we had to increase the bottom friction and the lateral friction at both straits in order to obtain a transport closer to the observed one. Moreover, following the work of Federica Borile, we are now working on a topographic wave drag parameterization, which is a modification to the equation in order to add a momentum sink due to dissipative wave generated by tides over the rough topography. How we do the validation of the tides in our models? We compare our observation with our model results with respect to observation, in particular EMODNet tide gauges data. Moreover, we also compare our result with respect to the TPXO, which is a global barotropic model. And this is important because it allows us to extend the validation not only to the location where we have the tide gauges, but also to the whole grid points of the model. Then, in order to compare to other numerical results available in literature, we also selected a subsample of 25 tide gauges, which results are common to all the reference in literature. In this first slide, we can see the validation results in terms of linear regression. In the upper plot, you can see for the first 3 tidal components, the comparison between the amplitude of the observed M2, S2, and K1 amplitude, and with respect to the model 1. What we can see is that we got very good results, and this is true for all the components. Here in the table, you can see the results of the linear regression also for the others, but we are a little bit underestimating the highest amplitudes, which are in Gibraltar and in the Adriatic Sea. Moreover, if we look to the phases in the lower plot, we can see that, again, gives the model gives a good skill in reproducing the phase, but we have some outlier. For example, this point which correspond to Messina, and this is because probably our horizontal resolution of the model is not enough to correctly reproduce the dynamics in this area. Moreover, we can see that we have other points out of the line. Usually these correspond to the points near to the amphidromic points, where we already said that it's very difficult to correctly reproduce the values of the phases. Then here I'm showing you the validation in terms of vectorial distance. What is vectorial distance? It is expressed through this formula, and basically it represents a way to include in a single number the difference between the modeled and observed tides, accounting at the same time the difference in the amplitude and in the phase. We can compute one vectorial distance for each tide gauge for each component. Here in the plot you have for each tide gauge, which correspond to the single beams, for each component which correspond to the different colors, the vectorial distance. This number is important because we can compare it with the literature results. For example, in the left table, we've compared for the first 4 components our result in terms of mean values on all the tide gauges with respect to two published results, Simplice et al. And Palma et al. What we can see that our validation results are very good, especially for what concern the diurnal components. Moreover, we compare to another literature result in terms of root mean square misfits, which are basically the root mean square vectorial distances. Here you can find the formula. And also in this case, we can see that our skill is very good, especially for the diurnal components. Moreover, here you can see the comparison, in this case only for the first semi-diurnal component and also diurnal component with respect to the TPXO model. Here on the left, you can see the amplitude difference. So here we have the difference between the MedFS model and the TPX model for all the basin, while on the right we have the vectorial distance, but in this case is computed between the MedFS and the TPXO values. What we can see is that for them too, the MedFS model is very close to TPXO. With the exception of the Gulf of Gabes, while for K1 component we can notice a bigger difference, especially in the Adriatic Sea. However, what I can say is that if we when we compared the results of the TPXO with respect to the observation, we found out that the MedFS system is closer to the observed values for the K1 component with respect to the TPXO. The first impact of tides on salinity that we can see is that we detected in our model outputs is an increase of the salinity in terms of basin average. This is shown by this time series, which represents the basin average salinity for the simulation with tides in red with respect to the one without tides in blue. If we look to the yearly mean differences between the simulation with tides with respect to the one without tides, at several depths. Here you can see at surface at 30 meters and at 150 meters, as well as if we look to this transect across Gibraltar, what we can see is that this increase in salinity involves the upper layers. And if we compare in terms of root mean square difference, we validate these two simulations with respect to in situ data, what we can find is that the error of the simulation with tides is lower with respect to the simulation without the tides. For what concerns the temperature, we still see a difference, especially close to Gibraltar and in the upper layers, but the magnitude of the difference here in the plot, you can see the time series of the difference between the simulation with tides and without tides. And again, in these maps and in this section, what you see are the difference between the two simulations. We see that the magnitude is very small. Here we are speaking about 10 to the -3 degrees, even if close to Gibraltar we can reach almost 1 degree of difference. But again, the simulation in which explicitly includes the tides show a better skill in terms of root mean square difference with respect to in situ data. This behavior is probably linked to what happens to the dynamics in the Gibraltar Strait. Here, what we can see from this table is that while the net value of the transport is quite close to the observed one, the incoming and outgoing values of the transport for the simulation with tides appear enhanced with respect to the simulation without the tides. This is probably linked, the fact that we see a more saltier and colder upper layer in the simulation with tides is probably linked to a modified mixing at Gibraltar Strait due to this enhanced value. Now let's move to the next topic, which are the Venice Acqua Alta events. In general, these events are defined as events of exceptional high of seawater level. The North Adriatic Sea, where Venice is located, is known to be exposed to this kind of events, which shows severe social and economical consequences. The contributors, the processes that contributes to this kind of events are linked to atmospheric condition at both basin scale, but also local scale. For example, here we can see for an event of Acqua Alta that occurred on the 12th of November 2019, a low pressure over the Mediterranean Sea, as well as a local storm on the North Adriatic. And if we look to the winds, we can see that during and before this event, Scirocco wind was blowing on the South and Central Adriatic Sea, as well as a Bora wind flowing and pushing the water through Venice. What is important to underline here is that it's important to have a model which includes the whole Adriatic Sea and not, for example, only the North Adriatic. Among the barotropic contributors, we find the surge, which is due to the low pressure pattern and high wind. Moreover, we have the tides, especially when they are in phase with the surge, like in the case of November 2019. As you can see, during this event, we have the maximum of the surge, and the tides are in phase with the surge. Moreover, what contributes an important contribution to this kind of events is given by the seiches. The seiches are specific oscillation modes of the Adriatic Sea. They are excited by Scirocco wind blowing from the south, and here you can find the period characterizing the main oscillation modes. As you can see, what is important to notice is that the periods are very close to the diurnal and semi-diurnal frequency of the tides. As if you remember, we said a few slides before that in the Adriatic Sea also the diurnal component is relevant. Moreover, to this kind of events, we can contribute also baroclinic phenomena, for example, internal tides or internal seiches, but also other baroclinic phenomena like local resonances and rapid waves can be good candidates to contribute to this kind of events. Our first case study for this event was the November 2019. Here, if you look at this plot, you can see the time series of the sea level at Ismarta gauge, which is identified by this red dot, and it is just outside the Venice lagoon. As you can see, on the 12th of November, the sea level reached more than 180 centimeters. The blue line in these plots represent our forecast, respectively the first, second, and third day of forecast. As you can see, our model was able to predict the Acqua Alta event 3 days in advance, because if you see also the line corresponding to the 3-day forecast saw the peak, but the peak was underestimated by all the forecasts. However, on November 2022, another Acqua Alta event occurred. What we can see is that in this case, the model instead was able to correctly predict the event since 3 days in advance. What is important to say is that in 2019, we were running a previous system version, which was not including explicit tides, and it was forced with the CMWF atmospheric conditions with the lower spatial and temporal resolution. So the starting questions on this work were how the MedFS was able to predict the event since 3 days in advance. Consider that also local forecasts were able to predict the event only a few hours in advance. Moreover, we asked ourselves which are the processes that contributes to this kind of events, and in particular, which is the role of tides among these, with the main aim of better understanding the underlying mechanism in terms of physics and to improve the predictability of such extreme events with our operational system. So what we did is a set of sensitivity experiments. So here in this table, you find the list of all the experiments that we ran, where we compared runs with different spatial resolution of the atmospheric forcings, runs with different temporal resolution of the atmospheric forcing, and runs with and without tides. Moreover, we compared our atmospheric forcing with observed data in Ismarta gauge in terms of mean sea level pressure, wind speed, and wind direction. Then we developed an FFT filter in order to extract and compare to observation the single contribution. Basically, what we do is to extract from the total sea level the tides, the seiches, and the residual which corresponds to the surge. Here again, the observation in smart tide gauge are in red, while the other lines correspond to our experiments. And what we can see is that all the contribution appear underestimated. Looking at the results of all the experiments that we run, what we can see is that all of these underestimates the main peak of the 12th of November of at least 22 centimeters and on average of 31 centimeters. But what we found is that if we increase from 1/8 of a degree to 1/10 of a degree the resolution of the atmospheric forcing, we improve our peak prediction of 4 centimeters, which is about the 13% of the 31 centimeters. Moreover, if we increase the temporal resolution from 6 hours to 1 hour, we improve of 3 centimeters, while if we compare the simulation with and without tides, we see a negligible difference for this specific case, but both the tides and the seiches are underestimated of about 6 centimeters. Summing all these numbers, we are able to explain around about the 65% of the difference that we see in our numerical experiments with respect to the observed values. When we compared the atmospheric forcing with respect to the observation, we found out that probably the fact that the atmospheric forcing underestimating the event is the main cause of this difference. Here what you can see is the mean sea level pressure observed in red, and all the other curves correspond to all available atmospheric forcing, and the same for the wind speed. As you can see, the CNWF prediction were not able to get the peak. Moreover, we went to analyze what is happening in depth during this kind of events. Here, what I'm showing you are the results of the currents in this red point, but we applied this analysis to several transects across the Adriatic Sea, and we are currently working also on density. Here in the first row, you see the results for the simulation without tides, in the second with tides, and then in the third with, you can see the difference. For the total current in the first column, the barotropic contribution and the baroclinic one, in order to analyze in depth what is happening in depth. What clearly appears is that there is a clear intensification of the baroclinic velocity before the event. Consider that in these plots we are analyzing the time series from 3 days in advance. The event corresponds to the black vertical line. So we can clearly see this intensification just before and during the event. What we can find looking at the difference is that this behavior is intensified when we include the tides. Because as you can see here, we see an enhanced current. Moreover, we can see baroclinic oscillations in both cases with tides, but also without tides. So these are probably seiches, internal seiches, which are enhanced when tides are included. So from this analysis, our hypothesis, this is an ongoing work, so we are trying to prove this hypothesis at the moment, is that the barotropic signal, in particular the sashes, interacting with the bathymetry, is converted into a baroclinic wave that moves toward the north, and here is converted back again to a barotropic sea level increase in Venice, which contributes to the Acqua Alta event. So, drawing a few conclusions on all these topics, we can say that despite their small amplitude, the tides play an important role in the Mediterranean Sea because they show a clear impact on the general circulation, but we can also say that they can contribute to some extreme events like the Acqua Alta one. Moreover, we have shown that the MedFS system has a good skill in representing the tidal sea level signal, even if the amplitudes are slightly underestimated in some areas, especially near Gibraltar and in the Adriatic Sea. And again, in some other areas, the phases, for example, near Messina, show a bias. But the main take-home message is that the explicit representation of tides contributes to the forecast skill of the MedFS and to the capability of the system to predict extreme events in advance. And that's all. Oh.
Many thanks, Anna Chiara. There are no questions so far for you. I have some from which I can start. So stay in the beginning of the presentation, the first part on the modeling system and forecasting system. How do you choose the number of tidal components that you want to include into the Med-Sea? There is any criteria based on dynamics that you want to resolve?
Okay, no, in general, for example, in literature, we can find a model which deal with 8, 4, or 6 tidal components in the Med. What we did is to run sensitivity preliminary tests where we compared run with 8 and 4 tidal components with respect to observed values, for example, in terms of time series, but also in terms of empirical distribution function. And we saw that 8 components are needed to correctly represent the tides in the Med-Sea. Moreover, if you include more than 8 components, the difference is negligible. So we choose to include 8 components.
Thank you. And you know, or you have an explanation of why the MED's forecasting system performs better than TPXO when you model the diurnal components?
Yes, this may be due to the bathymetry that we are using, because if you remember at the beginning, we said that some of the components are enhanced by interaction with the bathymetry, with the resonance phenomena and the interaction with the bathymetry. So the K1 is one of the components that is more sensitive to the bathymetry. So this is probably why in terms of the diurnal components, we performs better than TPXO.
Thanks a lot. And Federica Purilla made a question, and she's asking if there are any other points like Venice where you can analyze extreme events in the Med-Sea.
But in terms of Acqua Alta, is not only Venice, it's it concerns, it impacts all the North Adriatic. in general, for what concern extreme events, for example, we analyzed also the Medican Llanos, which impacted the Greece, but it's an extreme event. And again, in this kind of event, tides can contribute because they contribute to the dynamics, even if are not so relevant, such as in the Acqua Alta event, but it's a completely different dynamics. So yes, there are other areas impacted by extreme events, but I think that the Acqua Alta and the Adriatic is one of these in which the tides contribute the most.
Thank you, Anna Chiara. There is comments from Thomas Mohammed from University of Oxford. First, he congratulates with the fantastic talk that you give.
Thank you.
And I'm trying to summarize the question that he made. He's actually asking if there is explicit coupling between tides and surge. So if you have explicit interaction between the two.
In the Venice Acqua Alta event, no. In terms of barotropic contribution, there is no coupling. The tides just adds to the sea level contribution in order to increase the flooding, but the interaction of the tides with the event is in terms of internal wave. So probably the internal tides enhances the currents and what happens at depth, as we can see from the analysis on the currents here.
Good. And still from Thomas, I'm putting part of his question together with Stefano querying question that they're both asking how tides are explicitly represented. And actually what Stefano is asking details if it comes from the NEMO codes or if you implemented something by yourself.
No, the tides are included, as I was saying at the beginning, activating the tidal potential in the NEMO code. So all the all the modification that you can see of the system with tides with respect to the one without tides are already implemented in the NEMO code. You just have to activate the tidal potential, which includes in the equation the explicit tides. Then we had to provide the tidal forcings at the Atlantic boundaries. This is something that we built in a pre-processing phase, while the parameterization in Gibraltar and Messina and the topographic wave drag are something that will be added by us, modifying the code, which are not implemented in NEMO.
Thank you, Anna Chiara. From observation and previous work, there are a couple of questions asking, besides tidal gauges, and also TPXO model, if there are any other measurements from satellite or wherever that you can use for validate the system.
Yes, we use the satellite data to validate in general the sea level anomaly root mean square difference, for example. But here you can see a comparison, the result for the comparison between the run with tides and the run without tides. But we haven't used the satellite to explicitly validate the sea level, the amplitude and the phase in terms of amplitude and phase.
Another question is actually regarding the barotropic and baroclinic components. So how actually you decompose the velocity field into the two?
Okay. Wait, I'm moving to the slide. So I think you're referring to this. The barotropic is just the depth average velocity, so the average weighted with the level depth, while the baroclinic is obtained as with the difference between the total and the barotropic for each depth.
So they are computed as post-frozen from the total velocity. And there is a second part of the question from Hadi. He also asked, did you see any evidence of coastal crapid waves affecting the flooded regions?
For now, I haven't checked this kind of phenomena, but what I can say is that when I look to this kind of plots in these points very close to Venice, what I see is a reversed wave, a reversed current. So here during the event, we have a current going southward, while in all the other points, we have a current going northward. This means that we have some kinds of fronts which is formed during or before the events in this area, but it's something that we are checking now, probably with the analysis on the isopycnals. So what happens to the density, we will be able to understand in depth what is going on there.
Thanks a lot, Anna Chiara. There are other few comments. For example, if you know about previous works that show how temperature and salinity changes when you include tides into your model, especially at Gibraltar Strait.
Yes, one very important work is the one from Arzalla 2016. He shows exactly, he compares two numerical experiments, one with tides and one without tides, and he sees exactly the same behavior. So the tidal run with an increased basin average salinity with respect to the non-tidal one, and enhanced transport at Gibraltar. He ran his simulation for longer periods than ours, I think 50 years or something like that.
The last question before closing, it's about, again, observation. So how you calculate tides from observed data. I think Elisa is referring to tidal gauge, and how many years to use to do that. Okay.
First of all, we had to select from the whole data set only the reliable one. So checking the quality flag gaps and so on. So we reduced to 98 tide gauges. Here, the amplitude and the phase are obtained with the Foreman method, which is basically a fit with this kind of function of the sea level in the tide gauge, or observed at the tide gauges. We did a preliminary test, a sensitivity test on the length of the time series needed to obtain stable results, and we found out that we need 6 months, a time series of 6 months to obtain reliable results of amplitude and phase using this Foreman method.
Many thanks, Anna Chiara. We have no more questions, but there are many comments on the high quality of your presentation and answer. I think with that we can close. Thank you again for the presentation. And thanks to all the audience for questions and for the interest.
Thank you, Dorotea. Thank you all for the attention.
See you next time.